So you see the effects of the primary and the secondary interacting is very important. It affects the whole input impedance of the Tesla coil system, in this case a cylindrical coil. Great advantage of this is we've got very fine control of the tuning of the coupling, and we've got a very good balance between the electric and the magnetic, dielectric and the magnetic fields of induction, because we've got a very uniform, very linear arrangement of the primary and the secondary. Very little compression and magnification going on. So I'm going to bring slide that back down now, bringing the secondary back. There it is. Secondary starting to be in sphere of influence of the primary. So round about, let's just check the distance, just under 70 centimeters separating them. Coming back. Influence from the secondary, starting to get that splitting. Frequency splitting, which will become of course, although they already are, the upper and the lower resonant frequencies of the Tesla coil system. And we can drive power at both of those positions. That's a good spot there. And the loading on the primary means that the balance between those circuits is remaining very good. So the reactive balance between the primary circuit and the secondary circuit is close. That's a very good place to drive this coil system when you've got that reactive balance, and we got that by adjusting that primary circuit when they had a coupling of about 0.2 to 0.3. We adjusted the primary vacuum tuning vacuum variable capacitor so that we had balanced impedance between the primary and the secondary circuit. Those peaks were level. See, there are points it goes out of balance. It comes back into balance again there. I'm just going to take a measurement there. That's 40 centimeters. Great. That works very nicely. I'm going to pause that. Let's just check the balance. And I want to take, I'm going to save that result to use in my write-up. That's already in the minimum. It's good. There we are. 2.18, 2.22 and 2.26. That's a, we just check that again. I think that was 40 centimeters. Yes, 40 centimeters. Okay. So I'm going to save that now as well. As for consistency, we should probably get one at 30 as well. I've got a full set of data. 10, so 40. Right, so let's carry on, check our balance point, still pretty good. I'm going to bring it back down, back down. Frequency splitting is occurring more and more. Just check the distance, almost 30. That's at 30 centimeters. Check our balance. Okay, I'm going to move the markers again so we can have a look. A little tricky because the cube's so high. We're running at smallest number of sweep points here, so we can keep, for the real time, so we can keep the sweep high. We would find the Q, with a lot of points in there, the Q would be even higher than what we can see in this. But this is really an undamped resonant coil. It's very selective, very high Q. Good example of a well-built cylindrical coil, Tesla coil, for the kind of experiments that I want to do, which will be plasma experiments plus with the extra coil, some dielectric field of induction experiments, and obviously ultimately I'm going to use this for some more telluric transference of electric power as well. Okay, so we're now up to 2.15, 2.29. Let me just save this. That was at now 30 centimeters. Tuning I've kept the same. So it's also balanced. This is result 11, and that was 30. Okay, put it back into continuous. All right, I'm going to bring it back down fairly quickly, back down to what I consider to be the optimum drive point, which will be around about here. It's where you optimize coupling, so you get as much energy in as possible with maintaining the Q of the system, so the parallel impedance spikes are still high, higher than they were. I'm just going to retune that capacitance slightly to improve the balance. There we are, coming in now, there. Yeah. Very nice. Past the optimum point. Just making very small changes to the vacuum variable capacitor. Literally just nudging the wheel, exploring optimum space. That looks like a good balance point. Q's still high. Yeah. Very good. Okay. I want to see where we've come back to now. Looks like we're going to be back around about that 1.94. 1.93. Okay. All right, we've got that back to very optimum drive point, I believe. Just check the balance. Excellent. Okay, so we're going to take a measurement of that too. So now we are back to actually 7 centimeters, not 5. In between, I've adjusted the tuning capacitor, so I want to make a measurement of that as well. 581.6. Very close to where we had it before. I should think that coupling will now be around about 0.2. Everything else is the same. Okay. Now reading. Okay. All right. Good. All right. We'll just check that tuning again. Very good. It's maintained well. Okay. So what I'm going to do now is I'm going to leave that set in that balance position. This, as we said, was a good drive position. Get good coupling, so good transfer of energy from the generator through the primary into the secondary, with the same time maintained high Q, a good balance between the upper and lower resonant frequencies. We could use either of those as a driving point, either 1, 2 or 3, based upon the type of generator that we're using. And now I'm going to take the primary tuning capacitor through its full range of possible positions. So first of all, I'm going to take it down, increase the loading. First of all, though, I need to put it on continuous sweep. I'd already started turning it slightly, so let me wind it back to where it was. Okay, so it's around about here. That's our starting point, our balance point there. Okay, so now I'm going to start increasing the loading. See, now I'm emphasizing the lower frequency. If I was automatically tuning from feedback from the secondary coil to the generator now, I would definitely be oscillating at the lower frequency. That was now predominant. Winding it down, increasing the loading. Out of balance now. Obviously we've emphasized the lower. Put the primary and the secondary deliberately out of match balance. Increasing that load, I'm going to take it all the way so it's fully wound in. Right down at the lower point, and then we see what that looks like. Still winding it in. That's it. Fully wound in. Okay, so just change this slightly so we can see. Let me pause the scanning. No, we still can't see the peak. There we can see the peak. Okay, so let's put it on 1500. Bring all that way down. We'll get that right at the top. We have to zoom in a little bit further. Get that right on that point. It's a bit tricky. It's very sharp. There we are. Okay, so right down at 1.5 megahertz, right in the medium wave or the medium frequency band. Let's have a look at this. I'm going to look at the phase part of this now. We're still right at the bottom of the phase. Let's have a look at the impedance. Yeah, we're right in the bottom of the impedance. That hasn't changed. And then the upper, see the upper frequency is almost now completely collapsed. That point now is completely not emphasized anymore. It would be almost impossible in this situation to get it to oscillate at that point stably. That's now at 2.43, and the phase change, wire phase change, has stayed nice and consistent at 2.32, which we would expect. Good, so that's right down at the minimum tuning. So that's the lowest point that we can tune this system to. I'm going to save that, and we're going to measure the capacitance. 7 centimeter spacing remains consistent. I'm going to measure the capacitance of the tuning capacitor. It's 12538, so 1253.8. That's fully closed. 1253.8 puff. We can update that in the early results as well, where I should fully close it's around 1300, but we actually measure it specifically as 1253.8 picofarad, 1.25 nan, fully wound in. Take a copy of that. It's now result 13. It's good. Well, I'm going to plug that capacitor back in, and we're going to tune all the other way. So go back to continuous sweep. Nothing has changed much. It's all still in the same position. Now I'm going to reduce the loading capacitance all the way up to the minimum loading. It's reducing. The upper resonant frequency is coming back now. It's not suppressed so strongly. Gradually heading back towards the optimum balance point. We're going to move through the optimum balance there. Now we're accentuating the upper resonant frequency. Remember, that's due to the primary. We're seeing that primary move away now. So now, if we now set the tuning there, and we were taking automatic feedback to oscillator, linear oscillator as a generator, we would now be resonating stably at the upper resonant frequency. See that the phase change, wire length, doesn't move. Still at 2.32. That's because the overall wire length of this resonance system isn't changing by changing this tuning. If I were to unplug the wire at the bottom end of the secondary and plug a much shorter or longer wire in, then that would change. Actually, I'm going to unplug it just now. There. So I unplugged it, and you see now that secondary phase change from the resonant circuit in the secondary is now shifted up. I'm going to put that wire back in. There, it's back down again. Back down to pretty much almost a 2.32. Should take my hand away from it as well. That will also be damping the oscillation. Right back to 2.32. So continuing to wind up. See that peak from the primary, the upper resonant frequency is becoming huge now. We're even going to have to change the scale to see it all. Up to 2000. And there, to actually even see it. Going further, we still haven't fully unloaded. There will be a reach time, of course, where that peak from the primary will disappear off of the top of our scan, which is getting close to now. There. It's now disappearing off. It was heading back to its original position. Open circuit, if we remember, was about 7.7 megahertz. And there it is disappearing up. Bring it back down again, bring it back in. That wire change, phase change remaining absolutely steady. We've suppressed the lower resonant frequency. That's dropped right down now. That was the peak due to the secondary coil. Juicing, juicing. Back to the balance point. Somewhere around about here. Sort of scale back here. Go back to where we were. It's a bit much. Let's put it on the same as what it was originally. Oh, I have to pause it to get that. Put it back at 1000. Press this a few times. I'm going to have to close these. Okay, go back to continuous. So there we are. We're pretty much back to the balance point between the two. Just pause that for a sec. Take a measurement. Right back to the top there. 2, well, I don't need to change that. That's in the minimum. 3, that looks like it's on the top, pretty much. Okay, good. 1.94, 2.32, and 2.72 for the balance position. Let's just check the balance. Yeah, it's good. So there we are. That's a full tuning range and the full input impedance characteristics for this cylindrical Tesla coil set up at different coupling coefficients and different optimum points and taken forward through the full range of its parallel tuning that's possible for this. Represents a very flexible coil for the kind of experiments that we want to do with it. Okay, I think that's everything for this particular video, although I'm going to add another coil and look at the TMT properties of this too. But I'm going to do that in a separate video. Okay, so that is the Z11 AC small signal input impedance characteristics for cylindrical coil, varied both in parallel tuning, primary tuning, and also in coupling tuning as well. Okay, so I've now moved on to a TMT system with the 2 cylindrical coil systems. Previously we were looking at 1 coil system, so 1 primary and 1 secondary together. Actually we're looking at the transmit side of it. Now I've got a secondary system, so the receive system, we're again with 1 primary and 1 secondary, and I have those connected with a single wire connection at the lower ends of their secondary coils, and I have set them in an optimum position, or I've set them in a relatively balanced state, very similar capacitive tuning, loading on each of the primaries in the transmit and receive. I've got no load attached onto the primary of the receiver at this stage. And I'm looking at the input impedance, Z11, into the transmit primary in the same way that I was before. So now we have a TMT system up. The two coils are separated by a meter. So if you remember, that put them from the previous experiment out of the sphere of influence of each other if they're disconnected. When I took one coil system and I separated the secondary and the primary by a meter, they did not have an influence on each other until about 70 centimeters at the optimum tuning from the primary. So I got them 1 meter apart. Technically, of course, they are in the near field here. They're being driven in the near field to each other, given the wavelength that we're driving at them, which is just at the top end of the 160 meter ammeter band. And what we're going to have a look at in this is we're going to have a look at how a TMT system, how tuning affects a TMT system and the balance of that. And you can see already on the where I set it up here. Now, instead of 2 peaks, which we had previously when we're talking about one coil, we have 4. And we have interdependent coupling between that and the transmit coil and the receive coil, and also the overall wire length of the two together. So we are dealing with 4 resonance circuits here now, and all of those are intercoupled, and we have an overall wire length, which essentially in the TMT will also be related to the longitudinal cavity length, which is quite important. And in a transference of electric power, we are looking to balance both the transverse modes, that is the transfer of energy between the generator, the transmitter primary, and the transmitter secondary. That very much is about the transverse tuning of that transmitter. We're also looking at the transverse tuning of the receiver as well, getting that set up in a similar kind of way to get maximum energy transfer between the receiver secondary and the receiver primary and whatever load that we might have on it. And then we've also got to be concerned with the tuning of the cavity between them, whether that be in the near field, the midfield, or the far field. Obviously, the far fields are very much the Telluric transference electric power, and we'll be coming on to that in a subsequent post. It's work in progress and be reported in the future. Here we're looking at the near field, and we're looking at the balance of all of those things to get what would be for us an optimum TMT system in the near field for the transference of electric power. And I did those experiments previously with the flat coil. There are posts on the website, Transference of Electric Power Part 1 and Part 2, which look at the operation detail of that kind of system, but using flat coils. Now, flat coils are particularly good for dielectric induction field phenomena, and slightly less good for they are the dielectric induction field and magnetic induction field are imbalanced in that geometry because of the compression and magnification towards the center of the coil, and so the overall efficiency in terms of transference of electric power is not as good as a cylindrical TMT combination, or at least that's what I found in my experience, that the efficiency of the cylindrical TMT could be got up higher than that with a flat coil arrangement, and it seems to reflect from Tesla's work as well, where obviously the ultimate choice he seemed to make towards the end of his work was using secondary induction system, which is cylindrical, with an extra coil drive, part of his Colorado Springs experiment, which obviously was about telluric transference of electric power over large distances. So obviously we will be doing operational characteristics and comparison between those two systems, but first of all looking at the input impedance of this cylindrical TMT system, and also I will be in a subsequent post looking at the transfer characteristic Z11 of this cylindrical system as well. Okay, so having said all of that, let me have a look in detail here. So obviously we've got what was for a single cylindrical Tesla coil, we had a single peak at the lower and a single peak at the upper. Obviously now by connecting them together at their bottom ends of their secondary, I've coupled the 4 resonant circuits together. If I was to remove it, so let me just start this continuously sweeping and we see where we sit. I've done some initial balancing, so to get all of this, so we start at the balance point. It's not completely balanced, but that's something that we'll look into to see how difficult that is to do. But first of all, I'm going to disconnect the 2 coils physically from each other at the lower end. So I disconnect there and there. So I've now disconnected the single wire transmission medium between the 2, and we are now left just with the transmitter coil, connected obviously to the DGA SAQ vector network analyzer, the same as we were using before. I haven't changed any of that. Actually, I did this, doing this video directly after the previous one. So now we are looking, interestingly enough, at a unbalanced or relatively unbalanced cylindrical coil, emphasizing the lower resonant frequency here. So if I was driving this with feedback, a feedback oscillator, linear oscillator, then I would be definitely driving this at the lower resonant frequency. So if I reconnect that transmission medium between the 2, single wire, now we are also seeing the resonant circuits coming from the receiver. So the lower resonant frequency is split again into 2, and the upper have also split into 2 with their corresponding phase change reflecting those interactive resonant circuits. Let's just have a look at this wire length. When I take it out, of course the wire length changes. The cavity is now completely different. In fact, by removing the wire where I did, I actually even pulled the secondary of the transmitter out of quarter wave mode, because it was then open circuit at both ends. So if I disconnect it from the receiver, that's how it actually looks. So we see it's much more balanced now. So I've kept the transmitter secondary in quarter wave mode by taking the transmission medium out of the receiver end and not the transmitter end. Not perfectly balanced, but better than if I, of course, removed it from the bottom of the transmitter secondary. So it shows how much wire length and ultimately cavity makes a difference. I mean, this is now a cavity which extends from the upper end of the transmit secondary through there all the way down to the open circuit of the wire extension. And I can establish longitudinal mode or LND mode in that cavity. If I connect it back again to the receiver, okay, we've put the receiver resonant circuits back in again. We've got some imbalance there. But generally, that balance is quite good. So let's just set up our markers, and then we will look to see if we can improve the balance. So I'm not going to put markers on them all at this time. So the lowest is 1.77. I'm going to select that phase change point. 2.24. So obviously the wire length has gone up. So before we had 2.32 for a coil on its own. Now the combined cavity, remember they are reciprocal cavities. So this is a transmitter and the receiver that are counterwound to each other. They're not winded the same. So driven, both driven like that, they will obviously create a null in the center. If they are series driven by a linear supply, they will push against each other and create that interesting null plasma effect in the center. We'll be looking at the operating characteristics of that and the plasma phenomena in future posts. So that's the center point, and let me put this third one in the write-up of this. I will give a picture of this with all of the points noted. It just takes rather a long time here. So there we see what the range of the frequencies are, all the way from the lower all the way to the higher upper. So that's the lower and the higher upper, and the phase change. If I remove the receiver again, we see there's a significant change. Phase change 0.2 has moved, well, effectively the phase change has moved up. Well, everything is actually the lower has moved up and the upper has moved down slightly. Put that back in. Okay, so we're going to try and balance this a little bit more. I mean, we've got some slight emphasis to the upper and the lower in both cases. And if I adjust now the primary of the transmitter, so only very small changes. Really, just a fraction of a picofarad or 1 picofarad. So that's a better balance for the lower and the upper. They're not balanced between the lower and the upper, but the upper and the lower are themselves balanced. I'm going to also adjust the receiver, see if I can make any improvements on that. And I also need to, so that was, I think, optimal for the capacitors. I now adjust the coupling by just tweaking the spacing between the receiver, primary and secondary. There, that's getting pretty close. Very sensitive. The Qs are very high of these systems. They're very selective. In that respect, tuning them in this manner is quite difficult. It's very sensitive. Of course, with a load on, which I'll show you, that will improve. It becomes much easier when you put a load on the receiver because effectively you reduce the Q of these resonance circuits quite considerably. So I'm just adjusting the coupling of the transmitter now. Now the primary capacitance, this is very much a empirically determined optimum balance. So adjustments at the receiver to reciprocate what we were doing at the transmitter. There, that's pretty good. Not bad for a very high Q system. I'm going to take a measurement of that. That's very close to optimum balance. Let's see how stable it is. It's pretty stable too. Okay, I'm going to take a save of that. Let me just measure the spacings. notes of this. So we'll just measure the parallel capacitors for both the transmitter and the receiver. That's 604.2 for the transmitter. And for the receiver, and for the receiver is 649.8. 649.8. All right, we'll save that. We'll plug the tuning capacitors back in. We'll just take a reference. Let's see how well balanced that still is after we've fiddled around. Yes, pretty good. That's not a bad position. For the TMT system, you could definitely run that. I would expect to get reasonable transfer of electric power from the generator to the load. Take some very fine tuning, but you can only do that in operation, and obviously to adjust the cavity as well. So longitudinal cavity, that largely would be adjusting the coupling and very small amounts of tuning from both transmitter and receiver until we get that null point for the fields of induction in the center of our transmission medium, in the center of the cavity. So let's go back to continuous sweeping. Now I'm going to show the effect of changing the tuning quite radically in the transmitter. So I'm first of all going to increase the loading, and as we would expect, we start emphasizing the lower side of the lower frequency. So both the lower resonant frequency, lower peak, and the upper resonant frequency, lower peak, are both being offset. Those are being affected by the transmitter, and obviously the other suppressed peaks there are coming from the receiver. So in other words, we are biasing the system, the overall TMT system here, towards the transmitter. And if we were measuring our null point in operation, typically with a fluorescent bulb, or we have a bulb load actually in the single wire transmission, a visible load like that, we will actually see the load start to get brighter on one side, dimmer on the other. I've showed some of these already in transference of electric power part 1 and 2 with the flat coil arrangement, but we will see the imbalance, the energetic imbalance in the TMT system start to shift towards the transmitter. So herefore we are emphasizing the transmitter. We're going to be reducing the transmission or the transference of electric power. If we had a load on the end of the receiver here, that would be getting dimmer. And we're emphasizing much more towards the transmitter now. Continuing to increase that loading, I'm going to put the loading right there. You see the wire length remaining the same. Okay, so that's full loading. That was around about 1258 picofarad on the transmitter. Nothing's changed on the receiver. I haven't changed the loading on the receiver. So I'm now going to reduce the loading on the transmitter progressively. It'll head back towards that balance point that we had, where we've got good matching between the transmitter and receiver across that cavity, and we would be transferring a high efficiency of electric power from the transmitter to the receiver coil and ultimately into the load. So we're heading back there towards the balance point. Now I'm going to unbalance it the other way. So now we are reducing the loading on the transmitter, pushing it up, much like we've seen with just the transmitter on its own. There we are, opening, reducing that capacitive loading on the primary of the transmitter right up. Bringing it back down. So I'm going to take actually let me wind it first of all back up there. I want to take save these results. Let me export that data. That's the unbalanced case, which is a continuous phase. That remains the same, but the capacitive, this will have changed. Let me just measure that. Let me just stop this. I can't stop that. Cancel that. Pause it there. I have to unplug the tuning capacitor. Measure that. 147.8 puff. $147.8. Okay, we save that. We plug the tuning capacitor back in. Set it on continuous again. We're going to wind it back down, increasing the loading on the transmitter, capacitive loading on the primary in the transmitter. There we are, heading back towards balance, heading into balance here, just slowing it down somewhere around here. There is almost about right. And then we're going to head down. I didn't save a result right down at the bottom, so I want to do that. All the way down to the maximum loading there. Just going to pause that. We'll just take another measurement of this for reference. One, 256.3. Okay, so 1,256 picofarad, 1.25 nan, what we expected from last time. Okay. Disconnect the LCR meter, put that back into continuous sweep. So we're back where we would expect to be. Now we're going to wind it back to the balance point, and then we're going to have a look at changing the receiver. There we are, coming back towards that balance. Somewhere around about here. Could be tuned slightly better, but that's okay for this set of measurements. Okay, so now I'm going to do the same with the receiver load. I'm going to first of all unbalance it at the receiver, and we're increasing the loading on the receiver now. See, now we're accentuating those upper. You see, now it's loading on the receiver part of it, which represents this upper part of the lower. Before we were accentuating this with the transmitter, now we're accentuating this and this one by loading the receiver. Shows us very clearly how the resonance circuits work. There, we've almost gotten rid of that right down small there. So that's fully loaded on the receiver. So I'm going to take a pause on that. I want to get this data. I will need to check that and this. I didn't know where I had set back the transmitter. Let's just measure that. The LCR. 606.6 for the transmitter. 606.6. And at the receiver end, $1.2769. So 1276.9. Okay. Oops, I should have actually copied that. That was 1276.9, and this was 606.6. Okay, save that in. Okay, we reconnect those parallel capacitance, and I'm going to wind the receiver the other way. I'm just going to put this back onto continuous. Okay, now I'm going to unload entirely the receiver. We'll head back towards the balance point. There we are. You see the transmitter starting to come up. There we are, very close back to the balance point. We'd have to fiddle around with that considerably to get all of those very even. There again is a balance between the lower and the upper for the transmitter receiver in pairs, but they're not all the same height. We would have to adjust very sensitively both the primary tuning capacitors and the coupling coefficients to get all of those absolutely level. Okay, I'm going to continue to unload now. Now we're emphasizing those there, we've gone the other way. So now we've emphasized the lower parts. In fact, emphasizing the transmitter side, because we've removed the coupling completely. Well, no, not the coupling, sorry. We've reduced the primary capacitive loading down to only about 10-20 puff. So in effect, the transmitter is now dominating. And that's what we can see. If I measure that, let me just pause that first. So pause that. I'm going to measure the capacitance of the primary tuning capacitor at the receiver, so we know. 16.2 puff. So we've emphasized, we've completely almost removed the receiver. We're emphasizing only the transmitter by doing that. So let's export this data again. (16.2) and this remains 606.6. Make a copy of that. Okay, good. So we plug that in, we'll start the scan again. I'm going to bring it back to the balance point now. So I'm going to bring the receiver back in. Effectively, the receiver, for all intensive purposes, was removed by doing that. Now I'm putting loading back. I'm going to come back into balance. Oh, I've gone past. Bring it back. Okay, so right about there, I'm just going to adjust the coupling just slightly so we can improve. Bring that coupling to about there. Adjustment of the receiver again. Nope, going further away. Going further away. Okay, getting closer. It's not bad, getting quite close now. There, we're getting back closer, having adjusted both coil, very slightly the coil spacing and the tuning capacitors. Just a bit more. Tuning on the transmitter now. Somewhere about there. That's not bad. Okay, so what I'm going to do is I'm going to pause that for a moment. Well, actually I'm going to keep that and I'm going to add, well, I'm going to pause it and then add a load. So I'm going to put a load onto the receiver now. And that would essentially be, now I was doing transference of electric power experiments from the generator. I've got an incandescent load here, which is four 25 watt lamps set in series and parallel. There's a 100 watt load total, and I'm going to connect that to the output of the receiver primary, and then we see the effect that that has. Okay, so I've connected that across the output of the receiver primary. Let's go back into continuous scan. There, immediately we have damped down those resonant circuits, and now we can do some adjustments. So I'm going to balance it up. I'm adjusting now the tuning capacitor on the transmitter roundabout. So I'm going to put it about there, and on the receiver I'm going to adjust the receiver. So I'm emphasizing one side of the peak. You see down here I've got a double bow. Really I want to get that right down so it's the average of the two, and get rid of that bow there, like so. Now I look at adjusting the transmitter. Now it's overemphasized here. Getting better. Much easier to balance when you reduce the Q of the system, overall system. That's quite good. So we're about 1.78. This hasn't really changed much. 2.23. 2.65. And that's balanced with a 100 watt load on the end. You can get the impedances matched there. That's a reasonable, to the extent of the load there and there, they're contributing equally. The transmitter and the receiver. Wire length, of course, cavity isn't changing. Impedance is a little bit unbalanced. Magnitude, that is. Just push that up slightly to get a little bit more balanced. That's not bad at all. Split up a little bit. A bit too much. There, that's pretty good. Down slightly. Yeah, round about there. Must be a very good place to drive this in transference of electric power experiments. Put it on continuous. Let me do to find an optimal point. About there. Needs a bit of adjustment of the receiver. Yeah. About there. That's a reasonably good balance. It's these kind of small adjustments that you make to get the optimum energy transfer between generator and transmitter, and then the receiver and the load, and then adjusting, making fine changes, very fine changes to them both to get that longitudinal node in the center of the reciprocal cavity in the single wire transmission medium. Obviously in this case there will only, because it's in a near field, there will only be a single node in the middle. If we were doing this tellurically, obviously there will be many nodes based upon the distance between the two. Okay, I'm gonna take a okay, I'm gonna add that. Just going to make a measurement. .675 puff at the receiver. 675.0. We'll just measure that also at the transmitter. We see what we've got. Okay. What's that look like? 641.7. Okay, great. Let me just, I wanted to also check, I did make some very small adjustments also on this one for the coil spacing. Let's just measure that. Okay, so the transmitter is 7, receiver is 8. Save that, put it back on continuous sweep. Oh, I forgot to plug in the tuning capacitor in the transmitter, put that back in. Okay. Okay, so this is the small signal impedance characteristics and how you go about the tuning in a near-field TMT system using a pair of cylindrical coils. I would say their coupling, they're definitely set for probably between 0.2, 0.25. We'll be able to do that, obviously that accurately, that measurement, if we were also doing Z21. I'm going to do Z21 in the next post. Then we have a look at the transfer characteristics of the system, and these are connected by a single wire between the lower ends of the two secondaries, and we see that when we add a load, we obviously considerably reduce the Q of the system. I'm going to remove that again now. Okay, so that was with the load removed. You see where we get back to in terms of the balance of the system. To balance it again, we obviously make some adjustments on the primary. Obviously much harder again to balance this now because the Q is so very high. You're in effect balancing 4 resonators in this TMT system. We're getting somewhere back there, and really the measurements are this sensitive. So when you're actually operating this, say you're using a 1 kilowatt generator and looking to pass as much as get an efficiency over 90%, you are making very, very fine adjustments to get that much power between the generator and the load. Relatively easy to get efficiencies of 60% and a little bit above, but to get into very high efficiencies, even in an airfield with these systems, requires a lot of adjustment and tuning. Good. I think that covers everything now for the TMT Z11 measurements. And next, in the next post, as I said, we'll cover Z21. But good. That's the characteristics, Z11 characteristics of a tuned cylindrical TMT system.